Today's video is gonna be on Rift Lang. Rift Lang is spelled R for Romeo, I for Indigo, F for France, T for Tango, and Lang is spelled L for Lima, E for Alpha, N for November, G for Gold. Rift and Rift Lang is a flexible translator, and it's basically the video is gonna be on addressing what I'm going to do with Rift Lang. I want to start with what we're trying to achieve in this video. So this video, I'm trying to express a thread safe code as a theorem, which is equivalent for the same code with no locks and no semaphores in Python, or C in the target language. What does this mean? So I'm trying to create a theorem for a thread safe program that holds with no context. With the context. So so if there's a code that needs to it's a profiler, think of it as a thread safe profiler. So if you have a lock on the counter, and the counter locks, does that look, you need to lock this program at this state, it's a program, it's like a hypothesis, a state. It's not a hypothesis, it's like the problem is that there is a lock and a thread, and the thread can be locked with either a lock, which is a lock, which is a semaphore, which is like a semaphore is a shared lock, and we got a lock, a lock that delegates processes, that allows processes to run on a thread, So you got a semaphore, the share lock between threads. And my hypothesis is that, not my belief, is that, by by writing the format as a theorem, which a theorem is like something that holds true, like the Pythagoras theorem, first context, for locked and thread. We can have context addressable, context indicible. Okay, part of the problem is making sure that the system respects its own component. Right now, I've got my pen and paper, and I'm trying to express this formally. But the problem, what I'm trying to really do here. It's write a trusted program. So let me go to my thread save ZKP one more repository. This is overleaf, overleaf.com, housing and planning loan folder, overleaf.com. Sign in ORCID. I don't know about ORCID ID. I don't know about ORCID. I don't remember a lot of things actually. But I'm trying to find people who are on my level to express this formula. Openness@teaser.com. Yeah. So let me log in. I'm not logging to Quantum ZKP thread. One second. I found a document here I'm looking for. The RiFters way. Sorry, it's not quantum computing I'm looking for. ZKP. No, that's really proof. Thread. Okay. So let's go with the system of fault tolerance. Actually, this is all my work. I even forgot. Okay. So I'm looking at my screen right now. I haven't got the proof. So let's do one on paper. So, basically, I have to find the document later, but the document is very important to understand. And the paper I wrote, with the assistance of some, artificial intelligence, is about thread shifting. So think of Reflang as an interpreter. It's a translator for code, and you can take C code and port it to Python code, because it's not, it's like it's a trusted program, so it's basically available here. So let me show you my screen. I'm going to Noti here. Yeah. So here we have the repository I'm trying to build. So you're gonna have Reflang. So if you go to github.com/obnexus mk2 rift, because I locked myself out of the old repository, you have this repository here. So RiFtlang is a flexible translator. It's a meta compiler framework. That bridges pseudocode. It's not pseudocode per se. It's like instruction sets. So it's like it's like if you want to write your own code, you start from pseudocode, and that's the idea of the whole system. So Rift is a flexible translator. It's not Yak. So Luce knows what he's doing. It listens before it compiles. It's a problem. So let me just show you some examples. This is another good example. So one more trying to express. So RiFtlang is here. Oh, let's see what about this. So you get you have a system here. So you're gonna have pattern matching. So it's a pattern matching system. So Rift is different from LiftRang because LiftRang is a system that can be governed. So I'm trying to express that. Sorry. So let me switch back to the old the system. So what I'm trying to do. So let me read down what I wrote here. So. The theorem, for example, theorem is one of holds, like the drift theorem, the penalty theorem, and the theorems that I'm really talking about here is language theorems. Language theorems that exist in languages, theorems that exist in languages, and so a component. So let's start with a component. So a component for let's continue with component. So a component of a language or a Turing complete language is composed of component of a component which composes a Turing complete language uh uh that can be registered or packaged, registered and packaged in a component registry. It's a component registry. It's a schema. So a component expresses a schema. So what does this mean? So a component has the meta language type of token type, token value, and token memory. Token type of token, type of token, and you have token type or token kind. Token kind will be heterogeneous, homogeneous. Token type will be homogeneous, heterogeneous. So think of that as that's the only thing you can understand. A kind of token is falling into two kinds can be interpreted. So a kind of token can be interpreted based on the target language. It's like a Python or C. But explain this formally, you gotta know that something is there's something that you gotta understand. So token kind, token value, token memory, or token type, token value, token memory. There are two types of token in this. So, token type or token kind. So you understand now. So, the expression of this is a struct. Token memory is a struct. So everything starts from token memory, then goes to token kind or token type, and then token value. So it results in value lost. So you listen before you compile because memory is governed. It governs memory. So if you allocate memory in computer, with a bit field, you expect to use that memory, and before before if you add a bit to type of struct, a struct of integer, inside integer, you have a bit, you have in the memory. If I'm in the memory, and you can understand, memory is governed. Memory is governed. So it's contract between the token type and to the contract between token type, token value, token token type, token kind, token value, and actual memory that's being in memory. So it's a memory to token value evaluation relationship. At compile time and at runtime. No. As runtime, so basically, it is because you use the type of the token to assert itself. So you listen before it compiles. So it knows the value substitution constant between those two things. A component in a language is composed of a schema. A schema is written in length. So think of this way: if a JSON schema or binary or JSON binary, it's basically JSON binary, and this is binary equivalent of schema, and you open that schema, this is all in touch a screen. You run that schema. You are like you touch that binary scheme. Okay, let me give you a more friendly. So say you have a high level of JSON, and JSON is just a JSON file, just a common no not common related a colon development system, key colon value, comma, key colon value, and then this reference point. This schema represents a fundamental definition for the component registry. A component is a language, a Turing complete language, or not necessarily Turing complete, but part of Turing complete language. You can remember languages like language Noam Chomsky language, Noam Chomsky's grammar language. Okay, so I've got the evidence here, but today I want to take I have the theorem paper. Basically, the theorem paper was reducing the problems of thread safe to non-thread safe programs. You can say different program that evaluate the same, that does the same thing, but there's non-trace of the. Basically, it removes a lock or semaphore. And that's what the goal of this video was really to do. So I was going to demonstrate a program, but that removes a lock or semaphore, but has a new target point that's human readable program. It's not like the same Python code you wrote, but without with redundant locks removed and added, or you are. It's called a profiler. So it's a theorem. It's a thread safe profiler. I could have pluffer before, but it's a thread safe profiler. It's really just evaluates a theorem and outputs a new program. It doesn't spit out program, it outputs a new program. And that program is more efficient because the constructs have gone through error checks on the theorems of the language itself, such as the Python language or C language. So the component is like a package. So it's a packaged, it's a registered, it's packaged first and registered in an alpha numerical context addressable in the store. And so basically, what this means is like, a component. So this is my paper here. So this is my paper. So a component is registered. And a component such as let's start with this. So let's start with Python. So def hello. Let's def hello. Let's start with Python then, or Python. Def hello. Def is a name, is an identifier of a function. Hello underscore world, and this hello world colon has a statement called print hello world, come on world. This is a valid Python program in our written paper here. So the def keyword defines a function. The hello world defines the function name. So you got a keyword, you got a type of keyword, which is a function keyword, definition of a hello world, and you get a hello world. Hello world is a function identifier name, and you get the parameters, empty parameters or new parameters. Colon. So this is a parameter you call colon, and you get print hello world. Now print is a statement, but it evaluates your value. So it puts a statement. So basically, because it can be reached a statement. So think of it as a very exposure standard. This is a whole how it works. So if you have a statement is binary, true or false. True or false. Binary statement. Basic statements are binary. Why some of question? If the system prints hello world and printing hello world does not show on the screen, it's not a statement. Uh, uh, you know, uh, print hello world represents a statement, and basically I'm trying to use MucoOS to port RiFtlang, so everything will be literally left. So everything emerges as a component infrastructure. So it's part of the core infrastructure of MucoOS, informatic from like kilo of Oscar. Operating system, the world's first human rights operating system. The idea is to have dev hello world accredited as a system of theorems, theorems. So you're gonna have this is language. This is just a language construct. This is language construct. So you define a function called hello world, but this is not at the theorem level. So this is not at the profile level. Because this is basically at the profile level, but it's not at the thread level. So it's no thread in use here. So this program, def hello world, colon braces will identify as because it doesn't need to. There's no threat involved, so it's not necessary. It's not a method to this def hello world will print will be inlined. So it will be inlined because you can do the same with the same code as a single line in Python. So def hello world will be based on Python standards specification. Def hello world print hello world and end statement. End statement. There'll be no end. Because if Python can run in one line, they will not be minimized to that. So it's not long with minimize because it's a binary statement, and that statement is not optimized because it's a binary statement. It's binary true. You can still get the same print hello world. Print hello world. Because you can write it as one line. You know, so it stays the computer, the memory, humans in memory. But it's still readable. If you want to print, you just keep. If you don't need to so and you get expression. So if you have expression, the expression refers to a data model, a data there. So data refers to state and data. So expression refers to objects, ASTs, abstraction is like a representation of the data. You got an abstraction, which is basically a representation of the data. Of the program state, it's abstract synthesis. It's an intermediate representation of the program state of the language state, and it's basically you can have an AST of a functioning language at the parser stage, and like basically identifier language identifier. So you're gonna have a Alexa, which is basically a lexical identifier. Which one I'm talking about? You have to start the parser stage, so you can have an AST of the language of the you can have a representation, an intimate representation, an IR, which is not the AST, which is an IR, which is Lexa, IR, fed into the parser stage. And so you get the parser now, and you get the parser AST. But that IR interpretation for a program is fed into the parser stage, and that will transform the code or optimize it, reducing it while it's processing. Basically, it's like basically it's a. I don't think of it more of a as a just-in-time compiler model because it does the same function as just-in-time compiler. It basically it is a just-in-time compiler, but it basically produces the bottom-up top-down basically bottom-up parsing, which basically assert the type of the system via the framework of the system. So you get a bottom-up parsing which is basically bottom up, which is Cisco, basically Cisco, six instructions that and bottom up pattern will refer to the kind of idea that there's a structure that is bottom up. It starts from the bottom and right. So it starts from the bottom of the tree and identifies to go to so left right root, right left, right left, left right root order, and right. To right, left, you know, right or left. But it starts from the very bottom, and that's the breadth first search. No, breadth first search. But it works in layers. Breadth first search. And you get depth first search, which also works in layers. So you have depth first search with breadth first search, but you can have because they're different. You have depth first search, which basically goes down, but it works in layers. So it works in layers. So you can have the depth first search, which is basically depth first search. Uh, Bottom up system because that will let me see what's in the layers. We saw the layers first. You can have a breadth search, which starts from the bottom breadth, we start from the bottom and goes to the top, but not we across the chocolate, but not in the same layer. So layers went to the depth of the tree, of the actual tree the tree. So the actual tree the tree of the object represents the kind of state I'm envisioning for this project for my head. Uh, for what I'm doing here. Primarily, the goal is to have a theorem for so take a trustive program and output something that reduce the language into something that's readable by humans. But basically readable by human, but remove locks, add locks, add semaphores, or remove locks, remove semaphores. It's because it's trust safety is important. Um, Let me show you a program I wrote. So it's a context addressable a context indexable. So it's an alphanumeric context address. So think of this as so you can have a 0, 0, 0 x 0, 0, 0 x 0, 1, 0 x 0, 2. This is a decimal code within some of index address. If I have some address here and I reach a component. So this is a component. So this is like a JSON file. A JSON file. I brieflang compile JSON file, and I get JSON file here. So JSON file represents you know a schema. So it can be an XML schema or something, but it was a component, and this component has a language construct. written. I want to register from another language. So I load that address, but I load from that address. When you compare, it's everything's component. Think of them as Rust components because the components are indexed, are constructs, and they have the content, which is basically the language construct. So if I write a new pattern, if I'm making my own language in Reft, and I have a context address, uh, uh, I write the content. I don't write to it. I just read it. I just read it. I don't even have to read it. I just open it. And because you load it in a hash table, and because it's a hash table, 0000 presents one hash table 00001. It's gonna be put into a slot of the hash table, and it's gonna be loaded at 01. So it's gonna be placed in a slot, and then unless you want to unload it, and when you unload it, you have to put it back in. You have to recompile that component, and then load it back up. If you want to change edit some of the code base. So the language is basically so you can build a Gossy So Gossy is it's gonna be a Gossy but Lift and Rift are the core innovations of the language. So they're not Yak. The Rift is a flex and they're not Yak. So let me start to express this properly with you here. So we have here counter the pi. So this is counter the pi. This is counter. So counter equals 0. Shared lock, share resource. Counter lock equals terminal lock. So import terminal and import time, import random. If def increment counter, thread ID, print increment, global count. So this counter, global count is printing this counter. For I in range of increments, simulate some processing delay. So this is like a something that will have to come in time. So it has to be locked. So when this formation finishes, it's acquires lock and it runs the operation. So this is a fine lock. So taps and sleep is literally some process delay. So this is why locking is important. But this one doesn't need to be. This will be the same thing, but it has to go through a transpiler, and transpiler will take this code and transpile it to it. So this is an increment counter function. It points to a global counter for underscore in range. This underscore literally is not needed, and you can compile it for pattern specification for the code is. This is ignorable, so we don't need the value of this. We just want to do some processing. Can do should not be valid code here, pattern code. But for underscore in range of increments will basically be an input to increment function. And this will pop in here. So you're gonna have with a counter lock, temp equals counter. Temp plus 1, counter equals temp. So we create a temporary variable equals to counter. Temp equals plus equal to 1. So this is adding 1 every time. And this counter equals temp. So the thread ID takes an increment counter and counter of the increment and the count it in system. So you're gonna have the system here. So you're gonna have the system here. So you're gonna have a global counter, reset counter equals 1. So count equals 0. So global counter. So these are all pointing to global counter. So this is a shared variable. So this is a shared resource. They're shared between function two main routines. Routine, which are dev main and the code routines. But if the code routines can be paused and they're not being paused. So print thread ID equals counter with counter lock. So you have the counter here. Thread equals thread stop. So basically you have the counter, but you have the counter lock. So but the counter lock is not used here. Why? Why don't you use the counter lock? So it's locked. So it's a threading lock. So it's a threading lock. So threading lock. So there's a threading lock here. And as you can see here, can you see this code? Yeah. As you can see here, the increment per ID is increment by thread is 10. So thread equals 0. So thread equals 0. For I in number of threads, thread equals 10 equals thread equals 10 equals 1. R equals args plus 1. Increment ID code. So basically, you spawn a thread. So think of the thread spawning. So you spawn 10 threads. A number of threads 5. Maximum further of increments per thread 10. But they are basically they are one for number of threads. Number of threads. There's a thread the append and thread of stop. Thread append the thread. So this is a thread T and thread of stop. But this thread the start is literally the threads that start them. But they are basically this is keep a 1 to 10 to 50. and for 3 introduction. So this is thread. So thread is now running as one synchronous operation. So it's so Python can, so you're gonna have threads incremented counted to 1, 2, r equals 1. So thread ID is here, but the thread ID is 1. So the increment counter is value is thread. And this argues the increment counter. So this argues I plus 1, which is thread counter here, thread ID. And thread ID 1, thread ID 2, increment the thread is 1. So you're gonna have the increment here, and you have the threads here. So this is a function, this is code here. So you got the same equivalent in C, Python counter. This is a Python counter. And Python counter is a thread safe program. So, final counter. So this is the value of this thread or function. But, you're going to have a system, this code works. So this code does work, but you have the proof of concept. So this is the schema to the JSON, for packaging component. So you gotta understand this is all packageable, and the already said English you can build languages. So it's basically you take a language that can match with regular expressions. So you have an R syntax. So the R syntax is a regular expression engine, and so you're gonna write it's not pseudocode per se. You basically in C you match R uh, R colon R speech marks, and you push the expression there, and that is what's indexable. So usually you match between C IR and you have to use the regular automata. So you have the command C you can do. So let me just close the version and just show you what I mean. Let me just, can I just clone it? I can't even log in here. Can I clone it here? Uh, Come on, flies. Come on, fuck off. Sorry. CD public. CD public project. Okay, so let me just try to close the so right now I'm closing repository here, and as you can see, oh, phone number. So it's not letting me go SSH. So I haven't got some of the tools here, but dot slash build bin test client, test client. Yeah, this is not wide spoken. So I'm trying to find the power of the terminal. I know my code don't work. Yeah, so this is a terminal. Make 100% cd docs. Cd flag. Yeah. Can I just is it been a binary? This is a reflag. Yeah. Oh, it's no. Oh, this is a WSL. It's not fun. It's an XCB. It's XC here. It's not. So this is a reflag, and you have Windows sublist of Linux. That's D Debian. I have to start this WSL now. So so uh, uh so basically, my a lot of things are not have to be done with dealt with, but uh, it's like the problem is not even me anymore. So like I was saying to you, while this starts, the goal is to have a trusted program and a counter what a trusted program that runs its own principle. So where's my document here? I haven't lost the document. I hope. Tutor.com. Let me try to find it. Yeah, Fortran category. No, 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 this is a different paper. Where is it? Diagram? No. Quantum photo flash memory? No. Uh, natural language? No. Rubik physics. Warp drive? No. No, no, this is all my stuff. Yeah. I'm trying to find the Rift ecosystem. Let me find it with UKP. Basically, I had it here. Basically, the document I'm looking for is to do with Cisco. So yeah, I'm finished. So his statement, especially in sense, we got the intention. Basically, Cisco's command control and risk instruction set. You're gonna have that too. But these are all things to prove with the theorem to take with the theorem. So statement, expression, and intent are all hold. They all have a -1 state. They have things you have a consensus state of -1, or -2, or -3 that you hold together and never lose because you have to process this kind of system. So this Rift architecture, I hope it's this paper here. No, it's not this paper. It can't be this paper. So this is like this is all my possible issue. Uh, this is a continuum. It's not kind of like a incomprehendum. So I'm trying to have a quantum memory architecture. So basically, the all here physics quantum theory Rift theory. So Rift ecosystem, Rift 01. Basically, I found that the thread saved the documentation I wrote, but it's like it's basically a very like it basically works on kind of a system of basically it's a simple thing, but a thread. So a thread is like a thread. So basically, a thread has a thread like Oh, this is a this is one of my Feynman algorithm, Feynman diagrams. I love this one. Okay, so this is what I wrote, but these are all valid mathematics because this is just theory. It's not just on but it's like it's valid because it knows I know what I did with it. I know what to do. So a mod, yeah. So basically, it's called thread save ZKP. Let me try to find it on my patents, my other one. Because all of this has to come to production. All of this has to write a proof of concept. So, thread save ZKP. Yeah, there should be a paper here. Yes, yes. So this is the thread page ZKP document. So it's basically this is basically the any document folder. Trust yeah, thread page ZKP legacy. So yeah, this is the paper here. But it's a third string ZKP diagrams. This is the document here. So this is the some of the documents here. Sorry about this, but it's about architecture. It basically it doesn't need to even load on RAM because it already knows. It already knows basically. Let me try to find the. So this is all my papers here. So I'm trying to find that one document. So this is support. Basically, you have this is not the one I even need. But the term complaints. Basically, is it thread safe. Basically, this paper is like saying that the encoding of a system is like about the theorem. So it's a thread proofs. Is like the threads not they don't have side channels because they respect their own philosophy, and the goal is to literally just take a non-isomorphic lattice-based control. Basically, the system goes to everything is relative to a theorem. So if you can write a theorem, if you write a theorem and the theorem maps to a system, making it easy for everyone to use. You it doesn't matter you're human or not, or AI or you're human or not. You have a thread proof. So this is a thread proof. So let me try to find thread proofs here. So let me download this code here and work with it. So, basically it's a thread proof. Okay, thank you for watching this video, guys. Uh, basically, let me just see what I can view this on, on, on here. Yeah. So basically, yeah, this is document here. So this is a form of the thread proof, not some of the lattice so it's not even a quantum system. It is a no, this is a different paper, I think. No, this is not it. Okay. Thank you for this. This is not a problem. But the paper I wrote, it dives into how like you have a thread and you have a thread and you have a thread and you have a thread that doesn't lock it's not that it doesn't lock, it's that there's a thread safety and there's a thread lock and there's something that's thread safe. There's a boundary between the two threads. 1 second, I'm coming. Pardon? Okay, thank you.